Well, hello, welcome. This is our 12th lecture, isn't it? This is one for assignment 12. We're really going to get into doing some calculus today. So let's see, the first thing I want to do is show you the GeoGebra page that I was playing with last time. And I've added some extra stuff to this now. So one thing is that, as you recall, I hope you recall the slider here that has J as its name. That actually is controlling the x coordinate of a point on the graph. It's this point here, A is equal to J comma f of J. So that way its x coordinate is J and its y coordinate is the appropriate y coordinate to make you stick on the graph. So that's nice, right? You can slide that point around. Now there's another point visible on the screen, kind of following this running around as I pass it around the curve. What is that? That is a second point that's pushed off a little bit from the first one. And the amount that it's pushed off is controlled. Actually, in the book and in most places we use h as the variable for that, and forgive me, but I'm using k. What I'm doing is making k be an exponential decay function. So watch what happens as I change the value of this slider h. It makes k go closer and closer to 0 in a nice way. It has us flying in towards the point at first, but then slowing up and getting slower and slower and slower, and eventually getting almost to the point. There's actually still 2 points visible there when we're at the highest value well, the smallest value of that separation. All right, so what is going on in this picture? When I change J, you'll notice the green graph is, the green line rather, is a tangent line. That's been computed so that it does have the correct tangent. And if you want a little peek ahead, here's where that's done. We compute the slope, not the slope plane, but the slope as a function of x. And it's the derivative of the function f of x. That derivative has got to be done with respect to a variable. So we're saying derivative of f of x with respect to x. That's how you would read that GeoGebra code. But what it does is it tells you the right slope to have a tangent line at that x value. All right, so then so I've got this tangent line that moves around with the curve. I should probably actually, it'd be smarter if I turned these other things off for a moment and just let you see the point and its tangent line sliding around the graph as we move J. And it's kind of, well, that's what we're after, actually, is to find the slopes of those tangent lines, because they tell us how the output is changing when the input changes a little bit. Now, okay, so now I'm going to put the other things back in. B here is a point that is a slight distance away from the original point A in the x direction, and then whatever it needs to be in order to be back on the graph. So you notice how it's j plus k. K is that offset, and f of j plus k makes sure that we're on the graph. When our x coordinate is j plus k, our y coordinate will be the function applied to that same position. Now, the other thing that I had on here, and which I turned off, was that guy, this blue line. That's a secant line. So I think this relationship between the limiting value of secant lines and the tangent line is kind of interesting, and you'll get it when you see this animation played. The second point is moving closer and closer to the first point, and the blue line is drawing closer and closer to the green line. They have the same slope pretty much when we're done. I mean, I can only go so far because you'll recall if we went all the way to that point, we get a division by 0 error. But you see how they almost coincide. Let's stop the animation and move ourselves along to a different place on the graph. How about right there? Then we can start the animation over again. The green tangent line and the blue secant line almost coincide by the time we finish this loop. The animation is going through a looping behavior. It kind of depends what the particulars are of your location on the graph, how this limiting behavior will work. Like that, at that location, we stopped with a fair amount of difference, probably a couple of degrees of difference between the blue line and the green line. Whereas if we did this whole thing back here when j is equal to 2, they're already indistinguishable. So how quickly how quickly the slope of the secant line approaches the slope of the tangent line, that's a different matter. But that it does approach that slope is what we want. Okay, so there's a way to get at this slope of the this slope of the secant line, and so by taking a limit to get at the slope of the tangent line, and it's this. It's called the difference quotient. So let me show you the difference quotient. Okay, what I'm going to show you is two different versions of the difference quotient. The first one is when we have two different x coordinates in mind, an a and a b. They're both on the x-axis. The thing in the bottom here is how far apart they are. B minus a. Well, I'm making the assumption that b is bigger than a. The thing in the top is how far apart their y coordinates are, because f at b and f at a are the corresponding y coordinates that cause a point to lie on the graph. Let's finish this version of things first, and then you'll see it. Oh, and then we'll do the second one. See how far apart these points are from A to B? This is really the point A comma f of A. And this one up here, that's the point B comma f of B. But this horizontal distance between the 2 points, which is often called delta x. Delta is a Greek letter. You may have seen it in like fraternity and sorority things. It looks like a triangle, but it's actually the precursor to our modern letter D. Delta is used a lot in physics and other sciences to mean change in something. So when a physics guy sees delta x, he goes, "Oh, the change in the x variable." Similarly, there's a change in the y variable, and that would be called delta y. Now, what are these two things? Well, the first one is b minus a, right? The bigger number minus the smaller number, and the second one is f at b, minus f at a. And then our slope is the change in y over the change in x. That's a rise, and that's a run. Now, the second version of the difference quotient that I'm going to show you here, we play the same game, but with sort of different names for the two things. And it's only different in the sense of what it emphasizes. Think about x as being an arbitrary position along the curve. So we just call it the same as the variable that, this is associated with the x-axis, but I mean, x is a particular spot on the x-axis. X plus h is a particular spot that's a little bit farther down the x-axis. So it's as if that was x, the a became x, and the b became x plus h. And in fact, this version of the difference quotient, the function evaluated at x plus h minus the function evaluated at x, that's what's in the top, and simply h in the bottom. Yeah, well, how far apart are these points horizontally? The first one was at x, and the second one was at x plus h. We've moved over h units, so our delta x is h here. And our delta y, well, that's the difference in the y coordinates, which is f of x plus h minus f of x. Now that's basically the difference between these two versions of what we're doing here is name calling, but it does change the emphasis. See, here I think, okay, I've got two particular x coordinates. Here I'm working in general for an arbitrary x coordinate. It's weird that x is actually being used in a sense as a constant in this expression. X is thought of as fixed, and it's h that really is changing. As h changes, this point moves closer and closer and closer to the first point, the one at x. And so you get that behavior of the secant line approaching the tangent line that we saw in the animation. Right, these two versions of the difference quotient lead us to two calculations that people use all the time. I was going to cover up, well, might as well. The first one is called average rate of change, and you may, I certainly will do this, I'm sure, write AROC when I see that. AROC, the average rate of change. That's exactly what that first version of the difference quotient gives us. It tells you if you know where the thing is at a particular moment, and you know a second place where it is, again, at a particular moment, you can figure out on average how things changed. Sometimes the police use this kind of thing. If they clock you going by on one of these lonely roads and you're going 55 miles an hour, exactly on the speed limit, but they're at mile marker 100, and then 3 minutes later at mile marker 105, a buddy cop clocks you going by again at 55 miles an hour. Then they get in the car and they come and chase you down and they give you a ticket. Why? Because both of them saw the 55 mile an hour, but you went 5 miles in 3 minutes. You were going way faster than 55, somewhere in between. On average, you traveled, what is that, 5 divided by 3? It's about 90 miles an hour. In fact, your peak speed had to be really high because at the beginning and end of that little vignette I just told you were only going 55. So that's a way that the police can actually use to catch speeders. It doesn't work so great in populated areas like here in Connecticut, but out west they do this kind of thing. Get time checks on truckers particularly. Okay, the second version, modulo this, we have to take the limit as h approaches 0, but that second version is prime for giving us something called the instantaneous rate of change, and that you may hear abbreviated as IROC. There's also a thing in car racing called the International Race of Champions, IROC, but I don't mean that. Okay, so these this second thing really achieves a thing that's known as the derivative. The derivative of a function at a point So I'm sorry, I was doing that thing where I was writing, forcing you to watch me write, which is kind of wrong. Anyway, the derivative of a function at a point, so x equals a will be that particular input value we're interested in, is done by this process. You just take the limit with h going to 0 of that difference quotient, that second version of the difference quotient. Now I put a in for the x values rather than x values. You could do this in general. So you take the limit as h goes to 0 of f of x plus h minus f of x, that whole thing divided by h, and then evaluate at a. You'll get the same thing. I sort of like the second version better because, well, you're working in general, so now the same bit of algebraic work you've done can be applied at a whole bunch of different points. That seems, well, more efficient. All right, so we sort of have three different versions of the same idea going on here. The first of them, three views of the derivative. The first one is you're working at a point who's got an x-coordinate of a and the appropriate y-coordinate, f of a. The slope of the tangent line, that's what it means to find the derivative, is to find the slope of the tangent line. And it's given by this limit as h goes to 0 of our difference quotient. And that's with a in the spots where originally I wrote x's. The second view here for the derivative is what I've written here next. You're thinking in general. Right? For any x value, you can figure out what's the slope of this line that is tangent to the curve at the point x comma f of x. And it is given by this limit. Now that's the original version of the difference quotient that I gave you, f of x plus h minus f of x over h. Limit was h going to 0 of that expression. But look, compare these two things. How does the limit in number 1 and the limit in number 2, how do they differ? And literally, they only differ by the use of letters. This one had a, where this one has x's. We're used to thinking of x as a variable and a as a constant. I think you're probably used to that. But you know, you can use a variable or a constant in any way you choose. So one way to think about what's happened here is we've simply shifted our perspective, and we're sort of doing all the different a's all at once by thinking about this particular limit. It turns out the thing that's changing in the limit is h. So it doesn't matter what x is. X is not changing as you do the limit. It's only h that's changing. So that leads to a third way to think about the derivative. And that third way is to think of it as a process, or in a higher tone sort of way of speaking, it's an operator. An operator is something that acts on functions the way functions act on numbers. So this process, this operator, takes f of x as the input, and it produces a new thing that we call f prime. Now, f prime is literally defined to be the thing I've got written right up here. This limit as h goes to 0 of f of x plus h minus f of x over h, that is f prime of x. So we're going to see some examples of it, and I want to lead you through all three views of the derivative in these examples. All right, well, our example of the first type of thing is we're going to find the slope of the tangent line, but remember, that is exactly what the derivative is. We're finding the slope of the tangent line to function is y equals x squared, and we're working at the point 2, 4. I hope it's obvious to everybody that if I stick x equals 2 in, I get 4, so that'll be the y-coordinate. So there's the point, and just guesstimation, I would say it's a pretty large positive number, right? The slope there looks like it's kind of big. Let's see if we can figure it out. Well, yeah, we're going to use that first version of the difference quotient where the x is replaced with an actual number. What the limit is h goes to 0 of f of 2 plus h minus f at 2 divided by h. All right, but what's f? I just wrote y equals x squared, but that formula there, that's f of x. So the f is squaring, the function is squaring. So this limit can be rewritten. I think I have the wrong number of humps on that m. The limit as h goes to 0 of 2 plus h squared minus 2 squared divided by h. Now I want to take a second to make sure we're all on board with something here. If you make the following mistake, it's going to break a lot of junk. So make sure you don't think that this 2 plus h squared, it is not the same as 2 squared plus h squared. No, you can't just take the 2 and distribute it like there. A lot of people try to do that, but that doesn't fly. Think about it, if h was 1, 2 plus 1 would be 3 squared, which is 9. Well, what would this be? It would be 4 plus 1, which is only 5. Right? That doesn't work. What do you need to do in that situation where you have a binomial, let's call it, that's being squared? You have to kind of use the FOIL rule. You have to do a proper multiplication of this binomial times itself. So let's do that out. The hard part in this is just squaring 2 plus h. So first times first gets us 2 squared. Outer times outer is 2h, and inner times inner is also 2h. So that's a total of 4 h's. And last times last is h squared. And then I'm going to actually, what I've just done there is the FOIL rule of 2 plus h times itself. We'll be subtracting 4 from that. Oh, interesting, because this is really 4 as well. Right? And we've got h in the bottom. Well, now there's a lot of very convenient stuff that cancels out of this thing. The 4's gone. You have 4h plus h squared over h. Sometimes people will mess, this is another piece of algebra that people will mess up. This dividing by h, you don't just take it out of one of these. Both of the terms in the top have an h in them. You could imagine it this way, that you factor out an h from both terms upstairs, and then you have h times 4 plus h over h, and then it's those h's that cancel. So you end up getting 4 plus h. I prefer to just do this directly. Cancel this h with an h out of both of those terms. So my preferred route would be to not have to do that extra bit of algebra, but just say, okay, from here you get the limit with h going to 0 of 4 plus h. And that's a very nice limit to evaluate because you can actually stick h equals 0 into it. This is the sort of limit where the value of the thing at the limiting point, at 0 in this case, is the same thing as the limit. You just plug in. So we get 4. Because when h is 0, 4 plus h becomes 4 plus 0. Which is consistent with what I said before. Does this look like about a 4 to 1 slope? That's 1 unit, this is 4 unit. Honestly, it looks like it's a little more than that, but it's close enough for government work. Okay, so that was finding the slope of the tangent line at a particular location. Let's next do it in general. Take something that will ask us to find the slope of the tangent line in. So that's the question. We're going to find the slope of a tangent to y equals x squared in general, meaning at a point x comma of x, f of x. The function is squaring, so can I write x comma x squared, and people will be able to make sense of that? All right, so how do we do that? Well, we'll use the second version of difference quotient with x's in it, and we're going to be taking the limit with h heading to 0 of that difference quotient, which is x plus h squared minus x squared all over h. Now you're going to see this is exactly the same algebra we did the last time, except previously there were 2's where now there'll be x's. But the work proceeds in the exact same way. Limit h goes to 0. We have to FOIL rule out that. We get x squared plus 2hx plus h squared. Then we'll be subtracting x squared. That's from this last minus x squared bit. And then the whole thing over h. What things cancel? This x squared and that minus x squared are gone. And then let's notice that there's an h in the bottom and there's at least one h in both of the remaining terms. So this, you can actually divide out the h, which means that we will no longer have the division by 0 error when we plug in h equals 0 because it's been divided out. That is, you have 2x plus a single h. This can be evaluated. Stick in 0 for h, you got no division by 0 or anything else that could go wrong. You just get 2x. It's kind of important to notice that the where it is that you get to finally stop writing lim. It's right at this stage when you've actually evaluated the limit. You no longer have to write that lim thing because we're doing the limit now. We're saying the limit as h is heading to 0 literally is equal to 2x. So what's the last way of viewing all this stuff? It's as an operator. And what we had was a function x squared, and what we ended up with was a function 2x. Now, it turns out there's a really easy way to do things that look like x to a power, and we're going to learn this better the next time around, but let me kind of hint it at you right now. You'll see it again in the next lecture. If you have a power, x to the n, what happens in this process? Look what happened to the 2 that was in the power over here. It came out front. So you get that n will come out front. But we're not done. Here you couldn't tell that what had happened, but let's think about what power would be on this x. If there were a power, it would be the first power. So what has happened there is the 2 in the exponent has dropped by 1. So if we first multiply out front by it, and then we drop it by 1. That looks like x to the n goes to n times x to the n minus 1. An example of that would probably be in order. Suppose we had x to the third power. Here's what you do. Put a 3 out front and drop that power by 1. So it's 3 times x squared. So that thing is known as the power rule. And again, I said we'll come to it next time, but it doesn't hurt to give you a little hint as to what's coming. All right, we're turning now to something in the text. This is you got to watch out for the page numbering now that we're in the second book, because the page numbering works along with the numberings from the original book. So this is labeled as page 86, but look at the page number in the PDF, it's 138. So anyway, the thing on the page labeled as 86 is a big yellow box that's all about the derivative. And I hope you're used to enough of math books that when they put everything like something like that into a big yellow box, it means pay attention. This is a bunch of terminology and notation that you really need to be comfortable with. So let's try to start that process. You may want to come back to this big yellow box and look through things a couple of times to make sure you understand it. So the first thing they have in here is 3 different ways to talk about the derivative. The derivative is the operation that we've been just talking about. So the first one, the derivative of a function f at a point x comma f of x is the instantaneous rate of change. I personally would be happier if they'd said is the instantaneous rate of change of f at x, but that's fine. It's also true to say the derivative is the slope of the tangent line to the graph of f at the point x comma f of x. It's less true to say what they do in the third one, to say the derivative is the slope of the curve f of x at the point x comma f of x, because truthfully, slope is an idea that applies to lines, not to curves. And yet, that's what we're trying to get at, is a way to think about the slope. So maybe I'm just quibbling. This is an important word. It's not always possible to do what we're trying to do. That is, you may not be able to figure out a formula for the slope of the tangent line. Certainly maybe not at a particular x. It might not be possible. And if it's not possible, you'd say the function's not differentiable. And on the other hand, if you can do it, see how this says, if its derivative exists, you say the function is differentiable. Notation. There's 2 notations, principal notations anyway. They derive from the 2 people who invented calculus. The first one is called Newton-style notation, although Newton personally just used little dots on top of the variables. That evolved into primes because dots were a little bit harder to read. And sometimes you're taking the derivative more than once. If you have 4 dots, it becomes a little strain on the eyes to make sure you can see them apart. 4 primes is somehow easier, it seems. Anyway, that's Newton notation. We read that just, you just read it in line. You say f prime of x. or if it's y prime, y prime. Right? The other one, you read it as dy dx. Don't need to pronounce the fraction bar. Do you remember when I said that the delta y over delta x version of things was like the change in x over the change in y, and that delta was a precursor to our modern d? Well, Leibniz was just saying, let's use that typographic coincidence to sort of explain what the instantaneous rate of change is about. Replace the deltas with d's, and that's the one that means, you know, you've really moved all the way to the tangent line, and you're no longer dealing with a secant line slope. There is, let's see, yeah, I'm going to come to that. So that's Leibniz notation. I'm going to talk at the very end of today's lecture about these two gentlemen, Leibniz and Newton. It's kind of an interesting historical sideline. Okay, verb forms. We can say we find the derivative of a function, or take the derivative of a function. Those are synonymous. Or you can make it impersonal and say you differentiate the function. There's an adaptation of the Leibniz notation, dy dx, which means find the derivative of some new function. So it's d over dx of f of x. That's sort of viewing it as an operation. D over dx is the operation that says take the derivative of f, and what you call the result of that operation is df dx. They've thrown back in the formal algebraic definition. The limit is h goes to 0 of our difference quotient. That's what f prime means. That's also what df dx means. They're the same. Then they mention there's a practical definition, which is a little bit, in a sense, easier. You don't need to do any of the limits and do any of the algebra that might be needed to evaluate the limits. Just put in a really tiny value for h, and you'll be very, very close to the right value of the slope. Okay, so that's being very pragmatic. If you just need a close estimate of the slope, there's no need to go through all the work we're talking about. You just use the difference quotient with h tiny. Okay, so the people I wanted to mention. The first, Isaac Newton. I'm showing you a web page that's called the MacTutor History of Math Archive. It's at mathshistory.standrews.ac.uk. So that's a university in Scotland. Anyway, they have this great biography of all the I mean, there's literally hundreds of biographies of people in here, and I've got the font blown up real big so we can see the name well on screen, but it's a big, long biography and tells all kinds of stuff about the guy. He was weird. He was an unusual child, and he grew up into be an unusual man. But he was brilliant. He's the guy also famous for the story as the apple dropped on his head, and then he realized how gravity worked from that. He also did fundamental work in physics. He figured out the relationship between forces applied to an object and how that object begins to move. That's actually known as Newton's law. The unit of force in the metric system is a Newton. So, you know, his name has been attached to a lot of interesting things. He's also famous for being the first person to realize that light could be split up into different colors. There's a famous image of him holding up a prism and splitting the light beam from the sun into a whole rainbow of colors, which is kind of cool. The other guy, Gottfried Wilhelm von Leibniz, obviously a German. Newton was in England, Leibniz was in Germany, and basically it went like this. Newton had figured out calculus, but he didn't want to tell anybody else about it. He thought that, well, he used it as his sort of secret weapon to beat other mathematicians in contests. So at the time, this was a very popular thing. Somebody would pose a big problem, and all the world's best mathematicians would go at it, and whoever solved the thing first would be thought of as cooler than everybody else. They'd have bragging rights. And Newton was a killer at this stuff. And he became even more so once he realized what calculus was about. He kept that as his secret weapon, and he went to great lengths to make sure nobody else could figure out what he was doing. So he'd solve a problem with calculus, and then he'd go back and turn it into an argument about like Greek geometry that was, well, it was hard to do, but he managed to do it for a long, long time. Then this much younger gentleman on Leibniz, I wanted to show you these pictures of them. That's Newton. He looks fairly kind in that picture, and Leibniz, who looks a little bit mean and angry, but I think their actual spirits were quite the reverse. Newton was a fairly dour man, and Leibniz was friendly and shared his work. Anyway, these are pictures of the two people on stamps from the German Federal Republic. Newton is on the 100-cent stamp, and Leibniz is only on the 60-cent stamp. I guess that reflects the idea that eventually people decided, yeah, really, Newton did get this stuff first. But Newton was not the first to publish it, and that was where things got weird. Leibniz, once he figured out calculus, published it, started and told the world about it. And then Newton jumped up and said, no, I did that years ago, and it's here in my desk. He had all this writing on calculus in his desk drawer, but he never shared it with anybody because it was his secret weapon for kicking everybody else's butt in these contest problems. Anyway, that's became a great debate, and people literally challenged one another to duels over who was the first person to invent calculus, because it was a big deal, and it solved a lot of incredible and useful problems for people. So it's arguable that the Industrial Revolution couldn't have happened without the invention of calculus. Maybe a little bit, but it would have been, well, less good if they didn't have calculus to solve a lot of the optimization problems that they needed to do. All right, well, I think that's a good place to call it a day. Hope you've enjoyed this little foray into history, and I'll see you next time.